Okay, for this problem, we're looking at trying to come up with an exponential equation. So this is the numbers of polio cases in the world are shown in the table for various years. And it says down here the key part, let f of t be the number of polio cases in thousands, t years since 1980. So that's kind of the big point in trying to go forward with this problem is since it's since 1980, this would be 8, this would be 12, 16, 20, 25, and 27. So use a graphing calculator to draw the scattergram of the data. Is it better to model the data by using a linear or exponential? And the person who answered this said exponential, and that was correct. I'm going to go ahead and pull up the scatter diagram in Desmos. So I'm going to show you how to do that here. Let me grab this Desmos screenshot, or not screenshot, of this Desmos window. Okay, and I believe we can probably see enough. Let me drag this over a little bit. So if I hit the plus, I can go to table, and I'm going to go ahead and fill in that table. And the first one we said was 8, and that corresponded to 350. And I know this is kind of tedious going through this, but I've gotten some questions about how to put data in. So I'm trying to illustrate that now, just in a video. Then we said it was in 1996, so that was going to be 16 years later. And that's going to be 35,000 cases. And then we were at in the year 2000, so that is 20 years after 1980. And that was down to 6 cases. And then in the year 2005, so that's 25 years later. And they're down to 3.2 thousand, so 3,200 cases, 3.2. And then we're at 2007, which is 27 years later. And we're down to 1.3 thousand, or 1,300 cases. So that's a nice trend line. So if you look at my graph, I had this actually set up for another problem I did earlier. So I'm going to change my graph a little bit. I'm going to go the x-axis, I'm going to have it go from like maybe -5 to 30. How about we go to 30? So 30. I'm sorry, I didn't scroll over to show you how I got to this. So I'm going to drag this over, and you'll see this little wrench. I click the wrench, and that lets me change my window. Okay, so from here, the y values, I think to be more meaningful in how we see it, let's have the negative, so go up as far as 350. So let's maybe have go negative 20. That's not going to be enough. Negative 50. That's helpful. Yeah, you still can't see that. Let me drag this down. Okay, well, I'll just make it bigger. Negative 500. No, let's say negative. I guess go with negative 50. Sorry to be indecisive, because maybe it'll be helpful when I do change this one to 350 is the most, so let's make it to 400. There we go. That actually does come in. And you can see it looks like an exponential curve that's decaying. Okay, so that's helpful. And the next step, so I would agree exponential, would say, notice how this is x1. Let me drag this over. We have x1 and y1. So y1 tilde, the tilde on my keyboard is the button next to the 1. I have to hit shift, then that button, and it gives me the tilde. So that means like approximately a b to the power of x1. And that's a pretty good curve. I mean, yeah, that's off and that's off and it's a little off, but this R value is really good. And so they're telling us that it's A equals 2741.213 times B to the 0.773803 to the x power. So let me drag this out of the way. I can still see that on my next screen. So, well, this is the tough thing, because calculating this out is a little, these are slightly different numbers. So what I had come up with, this is what they came up with, and they probably used a TI calculator, but I'd come up with 2741.213 times 0.773803 to the t power. Okay, so that's how I would have gone about finding these values using Desmos. So I wonder why Desmos is, this is not the first problem that's been off a bit from what the TI came up with. So let me just confirm. I did 16, 35, 20 and 6, 25 and 3.2, 27 and 1.3, and then I had 8 and 350. So that's what I had. So that's what we come up with. And then for the next set of questions, the number of polio cases is, and this is I did a screenshot onto this, so that's the static, is going down. It's decreasing, I should say, by, so notice that's 77% or 0.77. Theirs was 0.74, but you do basically 100 minus the 77.38, and you come up with 22 points. Someone's going to correct me on this. 62, I believe it is. Let's verify with my calculator. Okay, 100 minus 77.38. Hey, I got it right. Okay, so then it says predict the number of polio cases in 2019. So this would be how many years after 1980. So that would be 39. Is that the problem? Did I make it? Oh, is this 2019? That's correct. Yeah, that's correct. So what I would do, I'm going to bring this back. So I would take a look at this and say, okay, what happens if x equals, what did you say, 39? And we could take this graph and drag it over and look at this. There are going to be a 0.12 thousand cases. So would that be like 124 cases? Again, we have a little different formula. Their formula must have given that 37. And then what year would there be one case? Again, let's go back to the graph. Okay. And hope there's nothing sensitive in the other screens when you see how it's up there. So what I'm going to do, make this bigger, and then I'm going to do y equals 1. And see where it crosses the graph. Oh, it's going to be not 1. It's going to be 0.001. I'm going to be way out here. Might be easier to calculate this by hand. Yeah, I think we're just happier to calculate this by hand. So if we said $2,741.213 times 0.773803 to the t power, when's that going to be equal to 1? We can divide by this 2741.213. So 1 over that equals 0.773803 to the t power. Take the natural log of both sides. take that t becomes a leading coefficient. So the natural log of 1 over 2741.213 equals t times natural log of 0.773803 divided by natural log of 0.773803. It's a 0.77. And t would equal, putting this in the calculator, you have natural log of 1 divided by 2741.213 divided by natural log 0.773803. And I get in 30.86967 years. So let's just say 31 years. Oh, I just saw a major error in my math. It should have been 0.001, 0.00, 0.00, 0.00. I know that because we're at 39 gave us 124 cases. Okay, and so I need to actually adjust my calculation, which is easy enough in the calculator to recall that last value. I'm going to go ahead and do second insert 0.00. Now, oh, there we go. It's going to be 57.807. So we could just say at 59 years or 58 years. So from 1980 plus 58 is going to be, was that 30? 2038. So I'm coming up with 2038 based off of our model, not their model. And then finally, half-life of this. So this is easy to do with the Desmos. Again, we're going to come back here. And so notice this initial value is 2741.213. So we could take that 2741.213 divided by 2. And I'm looking at 1370.6. So it's going to be an approximation anyway, but 1370.6 is what we're after for the population to have polio. So come back here. And I'm probably going to drag this way, not probably, I'm definitely going to have to drag this way back. I can zoom way out. There we go. And so I said, well, let's find out what it's going to be in when we're going to have a population of 1370. So let me go to y equals 1370.6, and it gives us this value right here, and 2.7 years. So 2.7 years, and it's not far from their model, so 2.7 years. And that's how I use Desmos to find these. Again, I'm not sure why they're coming up with a little bit of a difference in them. But that's how I do it. Okay, hope that helps.